So now here's the second example. We're now looking at a flow that approaches an obstacle. Okay. In a stratified situation, again, we have two layers, a light layer on top, a heavier layer. Okay, so there's a density interface in the middle. And in addition, each layer also has a weak density stratification. Okay, so this is how it looks like if you use contours, colors. Here, up here, we have the flow coming from the left, obstacle. So now what happens is that the flow creates disturbances and interaction with this obstacle. And the result are internal gravity waves. And they have a certain speed. They have a certain speed, and this is called the phase speed. So now what happens in this fluid, in this configuration, depends on the ratio of flow speed to phase speed of the wave. Compare them. It's called the Fruit number. Fruit number, it's defined here on the left side. Okay, and you can have different regimes. You have two different regimes and 1 point, a transition point. One is called the subcritical flow regime. This is when the Fruit number is less than 1. And in this regime, the waves can travel against the flow. Okay? On the other hand, Fruit number exceeding 1 gives you the supercritical flow regime. In this case, waves are carried away by the ambient flow. And the particularly interesting case is the hydraulic jump. And in this situation, waves can grow stationary. Hydraulic jumps means that if you have a wave, it actually has the same phase speed as the flow speed. And while the flow wants to move away the wave actually offsets with the phase speed this movement. Create a stationary wave. And this is how we set up the vertical ocean slice model, again using cyclic boundaries. Just starting with initial conditions, the flow is prescribed, and see what happens. Here are snapshots of the results. I show you the simulations in a minute. There are two different simulations, two different results, and the only difference is the speed of the flow that approaches the obstacle. Only the ambient speed is changed. In one case, you get almost no disturbances here in the interaction with your object, with your obstacle. And in the second case, you get a hydraulic jump and large amplitude stationary waves develop. Let's have a look at the simulations. The first one, you can see the arrows show you the velocity vectors, and you can see how from the side how the disturbances. You get some small waves, small amplitude waves, and later on in the simulation you get some effects by disturbances moving out on the right hand side, coming in on the left hand cyclic boundary. So how does the other simulation look? Let's have a look at that. See the development of stationary waves, as I told you. There are at the same location, and look at how big the amplitude of these waves. And these type of waves are called Lee waves. And now you get some interaction of the flow actually re-entering the model domain on the left side. Okay, so this is the example of waves and turbulence created in the lee of obstacle.